Hello, class. Welcome back. Today we are doing something called conditional probability. The concept isn't too difficult. Let's say that you want to find the probability of somebody getting uh, COVID-19, right? This is in the news, right? I don't really know what the probability is. It might be like, you know, 3% or something like that. But let's say that you want to find the probability of somebody getting COVID-19 uh, given that they are a nurse. Okay. So if you're a nurse, there's probably a higher probability that you're going to get COVID-19. Okay. So this word given makes a difference. So I'll think about the probability of getting bitten by a shark. That's going to equal something. But what about the probability of getting bitten by a shark if you're a surfer? Okay, this is probably going to be a larger probability than this up here. Okay, that's the general idea. And you can think of, the probability of getting into a car accident versus the probability of getting into a car accident given that you are a NASCAR driver, right? It's probably a higher probability that somebody that races cars is going to get in a car accident. So we're looking at the sample size, um, the sample space, I mean. So here we go. Family has two children, assuming that boys and girls are equally likely. Determine the probability the family has two girls. So um, you can have boy, boy, right? The first kid could be a boy, the second can be a boy. You could have had the first kid be a boy, the second kid be a girl. You could have had a girl first and then a boy, or you could have had two girls. So the probability of having two girls is this situation, and there are 1, 2, 3, 4 situations, so this is going to be 1/4. Okay. The probability of having two girls, if you know at least one of the children is a girl. So at least one of the children is a girl. That excludes this situation, right? So now we're looking at the probability of two girls if you know at least one is a girl. Well, that's again this, but now it's out of 3. So this would be 1/3. So we're restricting the solution set. How about two girls given the older child is a girl? Well, here the older child is a boy, so we'd get rid of that. In both of these situations down here, the oldest child is a girl. What's the probability of two girls? Considering the oldest child is a girl, right? The oldest child is going to be the first child. This is actually 1/2. So you can see that we went from 4 to 3 to 2. And just like the probability of getting, coronavirus, right, in New York might be like, whatever it is, 1 out of like 1,000 or something like that. If you're in a hospital, and maybe there's only 50 people in the hospital, it could be like 1 out of 50. It could be a bigger probability. So as we added more conditions, the denominator changed. Actually gets larger, the probability gets larger, like probability of eaten by a shark versus probability of eaten by a shark given you surf. So this is the word that's important, given. Okay, let's take a look at this chart, or this table over here. So we've got a whole bunch of males that they surveyed. They surveyed a whole bunch of female students. They asked them, are you going to college? Are you not going to college? The male students and the female students gave their answers. And this is the total number of male and female students here. So the total number of students going to college is 29. The total number of students not going to college is 23. How about the total number of males that are not going to college? Well, that's 14. These 14 people are male and they are not going to college. So probability of simply going to college is going to be 29. 29 people said they go to college of the 52. Probability of not going to college is going to be 23 out of 52 surveyed. Probability of male and going to college. Well, the male students that are going to college, right? There's only 16 of them out of all the people that they surveyed, 52. Probability of female and not going to college. Well, of the females, the ones that are not going to college, there were 9 of them out of the 52 people. This is where it gets different. Probability of going to college given they are a female. So in this situation, the restriction is we are only asking the female students. So the probability of going to college, given they're a female, 13 of the ladies said they are going to college, but it's 13 of the total ladies, not 13 out of everybody. So 13 women said that they were going to college out of the 22 total women. And these 13 people are female and college. And this is just female, right? Another way you can write this is F and C over F, or probability really. Okay, next one, male given they are going to college. In this situation, we only care about the people that are going to college. It could be male or female students. So we're going to look at only the people going to college. So the total is 29. It's going to be something out of 29, and we only care about the men in this situation. So it's going to be 16 out of 29. In this situation, we looked at the probability of being a male, right? And going to college over the probability of of just going to college. So 16 over 29. And the probability of going to college given they are a male. This is not necessarily the same thing. So we are looking at just the men, and then the ones that are male and going to college. So that's going to be 16 of the 30 men, right? So it's not, these are not always the same just because we reverse the order, right? Going to college, male, okay? They're not the same thing. It's like saying probability of getting COVID-19 given that you're a nurse. That's different than saying what's the probability that you're a nurse given you get COVID-19. Very different, right? You'd have to ask all the people that are sick and say, are you a nurse? Are you a nurse? Are you a nurse, right? So the procedure that I use in a table is I highlight the given row. I circle the first part in the probability. I put the first part over the total. So whatever the given row is, okay, then I circle whatever's there, and then the total would be somewhere over here. Okay, this is the formula for all of that. I kind of hinted at it before, but it is the probability of B given A is equal to the probability of both. I'm going to use the intersect over the probability of the given. And similarly, if you had the probability of A given B, you always just want to make sure that it's the second one that's in the denominator. Probability of B probability of A and B. So this is, again, red probability B given A equals probability of A and B over probability of A. Let's do another one with a table. The trick with these is that you need to total them. So 3 plus 2 is 5. So of the people that they surveyed, 5 of them have a sister. Of the people they surveyed, 21 plus 4 is 25. 25 don't have a sister, which leaves a total of 30 people that they surveyed. Of the people they surveyed, 4 plus 3 or 7 have a brother, and 21 plus 2 or 23 don't have a brother. Notice 7 plus 23 is 30. That has to work. So in a class of students, the following data table summarizes how many students have a brother or sister. What is the probability that a student has a brother given they have a sister? So the probability that they have a brother given that they have a sister, I'm going to write it out with the formula first. Brother, well, the order doesn't matter, but it's probability of brother and sister, okay, over the probability of sister. So for us, that just means that we're only looking at the people that have a sister. What is the probability that a student has a brother given that they have a sister? So of the people, you would basically say, imagine like saying, okay, everybody that's in this room that we surveyed, if you have a sister, we want you guys to raise your hands. Okay, so there would be 5 people total that raise their hands. And we'd say, okay, now keep your hand up if you have a brother. And 2 people would put their hands down, and 3 of them would keep their hands up. So this is this probability. I'm going to do another example in this using this table. Why let a good table go to waste? Let's say that we want to know the probability of, let's see, no sister given that they have a brother. Okay, so we're only looking at the people that have a brother. Everyone else we don't care about. And of the people that have a brother, of those 7 people, how many of them don't have a sister? 4 of them. Okay, given that events A and B are independent, let's say that they're not independent. You know, let me find a bet. I don't really like this problem, so give me a second. Okay. Okay. Okay, this is a much better problem. Give me 1 second, I'll be right back. I have to plug in my computer. Okay, back. Really don't feel like editing anything, so I'm just going to jump right into this problem. Given the probability of A equals 0.5, the probability of B equals this, probability of A and B equals this, find the probability of A given B. The probability of A given B equals the probability of A and B over the probability of B. We just have to substitute values. They tell us what the probability of B is. It's 0.71. And they tell us what the probability of A and B is. It's 0.415. This is what we don't know. Notice that they gave us this in case we wrote the formula incorrectly. So this wouldn't be correct, but if we would have written probability of A and B over probability of A, we would have been able to get some sort of answer, but it would have been wrong. So this was called a red herring. You just use your calculator to do this division, and we've got 0.415 divided by 0.71. That equals 0.5845704. The nearest thousandth is 10, 100, 1,000. We need to round up because of the 5. So the answer is 0.585. Probability of A given B. So that lesson was about 18 minutes or so. I'm going to put some delta math problems like normal. Actually, let me do one more. This symbolic probability rules. Let's see if we can figure this one out. So we've got, given that events A and B are independent, okay, the probability of A, so if A and B are independent, that means that the probability of A and B equals the probability of A times the probability of B. Keep that in mind. So they want to know the probability of B given A. Now watch what happens. Probability of B given A is the probability of B and A over probability of A. But since the events are independent, we can rewrite the numerator as the probability of B times the probability of A. And we've got the denominator as the probability of A. And these can divide to make 1. So the probability of B. So if they're independent, this formula holds true. Okay, it simplifies. All the other ones that we did earlier weren't independent, because if you work as a nurse, you are potentially more likely to contract coronavirus, right? It is dependent on the fact that you are a nurse. But if the events are independent, the formula breaks down simpler. So let's see. They want to know the probability of B given A. So the probability of B given A is just simply equal to the probability of B, 0.6. Right? I just substituted 0.6 for 0.6. So now you should be able to do all the delta math. On Tuesday, we'll have, Tuesday we'll have a live webinar, but it's going to be using Google Hangouts. I've never used Google Hangouts before, so I'm assuming that it's not going to go that well to start. There'll probably be some growing pains with it, but it's going to be the same standard week that we have. Probability unit will be over this week. If anyone has any questions, wait until the webinar to ask me. And if you still have questions, you can hang around after the webinar or send me some emails. Have a good day.